Hello and welcome to lesson 19 of this Introduction to Probability of Wolfram U. The topic for this lesson is the multinormal distribution. Let's begin. The multinormal distribution is also known as the joint normal or the multivariate Gaussian distribution. It's the multidimensional generalization of the normal distribution. It was discovered by the Russian mathematician Alexander Lyapunov as a generalization of Laplace's work. It's frequently used to describe unknown multidimensional datasets. You'll see how to compute multinormal expectation, probability, estimation, and simulations. How would you write the PDF of a vector of normal distributions? Like the normal, you expect a normalizing factor, a base e, and the exponent pi/2. So you can replace x and the mean by vectors to make it multidimensional. But is that it? Almost, but not quite, because you're missing the variance, or its multidimensional form. Okay, enough guessing. Time to face the beast. This is the multinormal PDF, where x and mu are vectors. But what happened to the variance? It became the covariance matrix, denoted by the uppercase sigma. Since it's a matrix, it complicates things a lot. If you know your linear algebra, you'll know not every matrix is invertible. Yet this distribution requires us to invert it. Not every matrix has a positive determinant, but this needs it since we're dividing by the determinant. So the covariance matrix of the multinormal has some restrictions. It must be positive, definite, and symmetric. As an example, here's the multinormal PDF in 2 dimensions, also called binormal. And yes, it gets complicated very fast. You can compute the multinormal distribution using the built-in multinormal distribution function. Here I use contour plot to easily visualize with control over the mean and correlation. Considering how complicated the PDF was, you can guess the CDF is going to get even more complicated. In fact, simplifying the integral algebraically is impossible in most cases. So let's just stick to visualization on this one, with the same code, modifying PDF to CDF. Intuitively, the multinormal distribution has a vector for mean and variance for each dimension, and a matrix of covariance, where the diagonal of the matrix is the variance. This makes sense when you remember that the variance is a special case of the covariance. The multivariate central limit theorem states a sampling distribution is approximatively multinormal even when the subdistributions aren't. In practice, data is often multidimensional and assumed normal. So this distribution is often used, and it's often reasonable in many vague contexts. The multinormal distribution is frequently used both correctly and incorrectly. So try to use it when the event measured is continuous and multidimensional, but most importantly, you should be able to determine or assume the normal distribution on every single dimension to be able to then apply the multinormal. So, time to apply. At this point, you should be very familiar with these problems. So I'll go a bit faster and you'll see if you follow. First, you want the probability of x is greater than 2, 3 for the multinormal of the mean 1, 2 and the covariance for 1, 1, 2. And that's about 11%. Then the probability that the sum of x 1, 2, and 3 is greater than 40 within the multinormal of mean 10, 10, 10, and this variance results in about 4%. Then what's the expectation of x1 power 2 plus x2 with the multinormal of mean 1, 1 and the covariance for 1, 1, 2? That's 6. If the three radius measurements of a styrofoam ellipsoid, that is, an ellipse in 3D, are normally distributed considering this radius and covariance, what's the expected volume? If you're not sure of the volume formula for ellipsoids, you can always ask Wolfram alpha. Okay, so take the expectation of 4 on 3 pi ABC, for ABC are part of the multinormal with the parameters from above, and here's your volume. Consider a light bulb factory. The bulbs it produces have normal distributions for lifetime and luminosity, seen here with their covariance. What's the probability an arbitrary light bulb lasts more than 550 hours and has more than 850 lumens? Let's assign the deviations to variables. Alright, so to reformulate the question in code, you want the probability of more than 550 hours and more than 850 lumens, as they're multinormally distributed over this covariance. And this significantly better than average light bulb will only occur about 6% of the time. As usual, to simulate data, use random variates. To visualize, use histogram 3D for data and plot 3D for the distribution. Last lesson, we estimated the wine fixed acidity was normally distributed. Can you estimate both fixed and volatile acidity? Okay, well, you can load the data, estimate the distribution on the multinormal, and confirm the relationship by plotting the data against the distribution. This indeed seems reasonable. So let's summarize. The multinormal distribution is continuous, multivariate, and bell-shaped. Its PDF is the vectorized version of the normal distribution PDF. Use the multinormal distribution, probability, expectation, random variates, and estimated distributions functions for any multinormal situation. But the assumption that every single dimension is normally distributed is often too simplistic. What if the second dimension is discrete or exponentially distributed? As you can imagine, the possibilities of combinations are endless. Now that you have a good vocabulary in terms of the popular probability distributions, it's time to transform, mix, and join those distributions to fit any situation, as seen in the next lessons.